Hello and welcome to the second part of the lecture. Now we are going to take a closer look at the inference computation in LLMs and identify the challenges associated with that, and also what are some strategies to mitigate those challenges. By inference, we mean taking a trained LLM and giving it a query or a question and getting back an answer fast enough and which is accurate. We are going to consider decoder-only transformers that are autoregressive in nature. Inference, as we'll see shortly, is computationally, it's very different from the training process of LLMs. And it does not enjoy the high degree of parallelism which is associated with the training process of transformer models. Because they are autoregressive, so the LLM generates one token at a time, and at every step, it looks at all the previous tokens which have been generated to generate the next token. And because of this, because of the sequential nature, it's hard to parallelize inference to a degree which was possible for training. Recall that for training, due to the teacher forcing algorithm, we are able to process all the tokens in a sequence parallelly. An implication of this is that because GPUs are meant to speed up massively parallel programs, so if some computation inherently doesn't permit a high degree of parallelism, it will not take good advantage of the GPU. We will look at, given the challenges associated with inference computation, we are going to look at techniques to minimize the latency so that we obtain a response fast enough and it doesn't feel sluggish. We have good throughput so that the hardware is used efficiently. And also, we saw earlier that the dot product rotation scales quadratically with sequence length. So how do we overcome that to make long context possible? Specifically in this lecture, we are going to look at how KV caching prevents us from doing redundant computation, thereby increasing speed. How the inference process naturally splits into an initial prefill stage where the input prompt is processed and all the subsequent stages which are decode to generate a single token every time. After observing how decode is the main bottleneck, we will see how its throughput and latency can be varied by changing the batch size. So we will derive some formulas and we'll take a particular a real open source model, consider a particular family of GPU, and try to derive some numerical estimates for these throughput and latency values with respect to the batch size. In later lectures, we will look at other techniques for speeding up inference, namely speculative decoding, flash attention, and also how do we intelligently batch prompts together for increased parallelism. A nice perspective of inference looks like this, that we give an input prompt to the LLM. The LLM returns log probabilities over the vocabulary from which we sample the next token. We append the next token to the input prompt and then process everything together again to get the distribution over the vocabulary again, and so on and so forth. The problem is that in this whole process of inference, its complexity is order n square flops if we just consider the position-wise MLP. And for the self-rotation modules, it's order n cube, where n is the number of tokens totally generated. To see how that happens, consider this particular stage. Let's say that there are j tokens which go as input to the transformer model. The position-wise MLP in each layer acts on each token individually. So summing up all the layers, it's still order j, where j is the number of tokens in the sequence here. And adding up j going from 1 to n, that makes it order n square. Whereas for if you consider in a particular layer the self-attention module, every token is going to attend to every other token. So in this particular stage, it's order g square. And if you sum up g going from 1 to n, that makes it order n cube. We can improve things by observing how we are doing redundant computation. Because we have an autoregressive model, so any token attends only to the tokens which come before it. And so we can observe that once we, at any point, we compute the query key and value of any token, it doesn't change with any tokens which come later on. So for instance here, once we have computed the key and values of x1, x2, x3 and x4, then no matter what token gets generated later on, their keys and values won't change. And in the next stage, I'm going to need their keys and values. So I might as well store their, as and when I process these tokens, I can store their keys and values in a data structure called the KV cache. So K for key and V for value. So consider the first step where the LLM processes the user query, which is a sequence of tokens here. And we are looking at, for one attention head, we are looking at the dot product attention computation here. So associated with each token, we have a query vector and also a key vector and value vectors. So in dot product attention, effectively we are doing multiplying query with key, scaling, then masking for autoregressive model, applying softmax, and then having this attention weights. We are doing a weighted average of the values to get the results. Here we have not shown masking and softmax for simplicity. So this is there. Now what about the stages after the first one? So here this is the very first stage. We are processing all the tokens in the input. Well, this is what we call the prefill stage, and after this we can save all the computed keys and values in the KV cache. And at any subsequent stage, all we need to do is generate the query key and value, the ones in green, for the last generated token. And we can make use of the keys and the values of the tokens which were already generated. So retrieve them from memory, and then we do this computation to get the new result. So we didn't have to compute the K's and the V's of the previously generated tokens. And observe also how we don't need the query of the previously generated tokens. We only need the query of the last generated token. So all of these stages, apart from the first stage, those are called decode, where we are processing only the last generated token and we are outputting a single next token. And as this goes along, once in this stage we computed the keys and the values of the last generated token, we add it to the cache for subsequent stages. So now our inference process looks like this, that we give it an input prompt and the transformer processes all these tokens in parallel for the prefill stage. Whatever keys and values were generated in each of the layers, they get put in the KV cache, and the output is a distribution over the tokens in the vocabulary from which we sample. And in the next stage, all the transformer needs is the last generated token and the current KV cache, and it can generate the next token and also augment the KV cache by adding in the keys and the values for the previously generated token which were computed in this stage, and so on. And with this, Now our complexity changes to order n flops for position-wise MLP, because in each stage we are doing only a constant number, so we are just acting on one token per layer for the MLP, and the self-rotation changes to order n square for the whole process of generating n tokens. And this is because in the self-rotation, this operation of multiplying the query with all the keys of previously generated tokens and then multiplying addition with the values, this is order n. So if you add it up over going from one, like over n total n generated tokens, it comes to order n square. So if the response has n tokens, it means that we are running n forward passes on the transformer model. And this means that we first did a prefill stage, and every other n minus all the rest n minus 1 stages, they were decode, which made use of the KV cache. So prefill and decode stages, although they are both part of inference, they have very different computational characteristics. And we'll see shortly that prefill is compute bound, and that is good. We want kernels running on the GPU to be compute bound, but decode is usually memory bound, and this is bad news. So we don't want to spend time moving things around in GPU memory. We rather want it to take more time to compute. In a way, prefill looks a bit like training. It has the same high degree of parallelism which training has, but prefill is only the first stage of inference, or everything else is decode. So that's it. And to see how prefill is compute bound and decode is memory bound, we are going to adopt the same approach which we did in the last part, and we are going to decompose the operations happening in a transformer layer to one of three classes. First is the linear operations, the matrix multiplications for obtaining the query key and value embeddings, and also to get back the output projection for each head, and then also in the MLP to do the position-wise feed-forward computation. Within the self-rotation module, we'll separately consider the dot product rotation, which is the inner product of queries and keys, along with softmax, and then doing a weighted average of the values with the attention weights. And everything else like layer norm and activation functions like ReLU and so on, they can be mostly ignored for our analysis because they take up only a tiny number of flops. So we'll do a quick recap of arithmetic intensity of matrix multiplication. So consider multiplying this tensor in BS16 of this shape, which you can think of as activation, by BS16 of matrix of weights. So recall that we saw this in the MLP. So this was X, the input to the MLP, and this was the linear operation in the first linear layer in position-wise feed-forward network. Now, if you recall the diagram computation flow which we saw earlier, within the attention layer, the parameters of the projections, they had the shape of D times NH, but the analysis which we're doing now, it's very similar to what will be there even for these projection matrices. So multiplying these two tensors, it takes up these many BSDF flops. So multiply all the dimensions, don't repeat anything. And the memory transfer we'll have to do is we'll have to move this in memory, we'll have to bring this to memory, and then we have to store the output back to HBM. And so to be compute bound, we want this ratio to BSDF flops upon bytes to be greater than the ops bit ratio of the GPU. Now, in LLMs, D and F, so D is the embedding dimension and F is what's called the hidden dimension of the MLP, and they are usually quite large. So we can assume that D and F is much greater than the batch size of a particular batch of samples going for inference. So our denominator, this quantity, we can approximate it to, we can ignore 2BSD and 2BSF because they are much smaller than 2DF for reasonable context lengths S. So not for very large context lengths, but for somewhat smaller context lengths. Now our condition to be compute bound changes to B times S being greater than the off-bit ratio of the GPU, where B is the batch size and S is the number of tokens in each sequence. Taking a particular GPU, if we get its ops bit ratio, so for H100, the throughput is 989 teraflops per second, and the bandwidth is 3.35 terabytes per second. So its ops bit ratio turns out to be 295 flops per byte. So for a matrix multiplication to be compute bound on H100, we want BS greater than 295. So let's consider the prefill stage first, and let's look at, first of all, at the linear operations, which are matrix multiplications. So we want B times S greater than 295. Now consider a single input prompt that itself is usually likely to be greater than 295. So we can even consider B as 1, meaning like we don't batch any prompts, and we will satisfy this criteria for linear operators to be compute bound in the H100, which is good. So this makes the most use of the GPU, and we are not bottlenecked by communication. What about the dot product addition? So in our earlier analysis, we saw that during the training phase, we derived these many flops for dot product attention. So recall that it's order S square in the sequence length. And as we also observed before, that inference flops is 1/3. So training is both forward and backward pass, and backward pass was twice that of the forward pass. So inference being only forward pass, it's 1/3 of this, which is 4 times BSS NH. The amount of bytes we are moving around to and from HBM, considering that everything is in BF16. So let's maybe go back to, so we are considering this operation here. So we have to bring in the computed query matrix and the key matrix from high bandwidth memory to the GPU execution units. So we have to transfer them. After that, the result of this whole thing, after masking and softmax, that is the matrix of attention weights. And that is quite large. It's because it's order S square. So that can be a very large matrix. But because of an algorithm called the flash attention, we don't have to move back that attention matrix from the shared memory of the GPU to the high bandwidth memory. Though that can stay in the shared memory, we can load in the V value matrix and compute the results. So we only need to account for bringing Q, K, and V from HBM to shared memory, and then writing out the result back to HBM. And this is what we do here. So we account for the K, Q, and V projections, each being of shape B, S, N, H, and because of BS16 we have 2 bytes. And then the output of this, again of shape B, S, N, H, each of 2 bytes. So we move around so much of data. And we don't write the intermediate result attention matrix of BSS shape back to HBM because of flash attention. So the arithmetic intensity of dot product attention for prefill, we divide flops by bytes, and that turns out to be S by 2. And if we have S greater than 590, then this arithmetic intensity is greater than 295. So dot product attention can be compute bound for prefill. And it's not so hard to make the input have sequence length, the number of tokens, be greater than 590. So it's relatively easy for us to make both the linear operation and dot product attention compute bound on the GPU. For the decode stage, recall that we are doing this operation. We are loading in keys and values from cache for the previous tokens. For the last generated token, we are computing the query keys and values. And then here's the output of the attention operation. So for the linear operators, let's look here. So we wanted B as greater than ops byte ratio to make linear operator compute bound on the GPU. During the decode stage, whatever matrix multiplications we're doing, S is 1 for each sample in the batch, because we are only getting the query key and value for the last generated token. So we are doing the projection only on the embedding on the last generated token. So S is 1 in this case. And so our criteria of BS being greater than 295 now becomes B greater than 295, which means that we want to do decode with a batch size greater than 295. And this implies that we are having 295 concurrent requests. We are batching them together. So we are having these many prompts we are processing together. And it's actually quite hard to be able to batch these many prompts. Among some of the reasons is that different prompts, they have responses of different lengths. And also, as we increase the batch size, we're going to see shortly, the latency also increases. And this leads to poor user experience. So it is a bit challenging to make the linear operations compute bound for the decode stage. We can do something. We can increase the batch size to some extent, and we'll see how to do it in later lectures to improve the arithmetic intensity of linear operations for the decode. For the dot product attention, consider, let's say that we already have processed S number of tokens before, and these can be coming from the input query plus whatever we generated in the earlier stages. And NH equal to D is something which we usually assume. So here, what are other operations which we need to do? So we need to read in this query embedding of the last generated token per sample in the batch. So the query tensor is of shape B times S is 1 times D, and because it's BS16, so it's 2 times here. So we have these many bytes. We have to load the computed Q projection, which we did in this stage, for the last generated token. Along with it, we also need to load in the key value cache of all the previously generated tokens. And K and V, they are of shape B times S times D, where S is the number of tokens which I've already processed. So because K and B are two tensors, so we have 4 BSD bytes for this. To multiply Q and K, we incur 2 times BSD flops. So for every sample in the batch, I am taking query of the last generated token with keys of S tokens. So we have this, and we don't consider saving the attention matrix back to HBM because of flash attention. It's still in shared memory, the A matrix. And now I've already considered loading the cost for loading V matrix here. So A times V matrix multiplication, that will incur 2 BSD flops. And then finally, I will write the result of this, which is a tensor of B times 1 times D. And because it's BS16, so these many bytes. So if we add up the number of flops, this and this, it's 4 BSD flops. And the number of bytes transferred, it's 4 BSD plus 4 BD. And the arithmetic intensity we get for dot product attention is S upon S plus 1, which is approximately 1 because S is usually somewhat large. And this is very far from 295, which we were aiming for. And even worse, there doesn't seem to be much we can do about it. Like, it's just a constant, a very low value. So the dot product attention during decode is always memory bound. And this is the challenge. There is not much we can do about it apart from reducing the size of the KV cache. And to see how that helps, observe how the denominator is dominated by 4 BSD and not by this. And 4 BSD comes from moving around reading the KV cache from HBM. And the problem is that we loaded such big matrices, but because of these because we're only processing the last token, in effect, we are doing thin matrix multiplications. So we are loading in a lot of data, but we are not doing enough flops for all that. So one way to improve upon this is if we can somehow reduce the size of the cache, then that will improve the arithmetic intensity. And in later lectures, we'll look at ways to make the KV cache smaller. There are a few metrics associated with inference, and specifically latency. So latency has 2 different numbers associated with it. Consider a user submitting a query to an inference service, and they receive token one after another, like this. The time between submitting the query and receiving the first token is called time to first token, TTFT. And the gap between subsequent tokens, it's called inter-token latency or ITL. So TTFT corresponds to the prefill stage and all the ITLs correspond to the decode stage. We can, for our analysis, assume that all the inter-token latencies for all tokens are same. So because the decode stage is the one which we do the most, and also because it's inefficient, we'll focus more on it and try to obtain some estimate of latency and throughput for it. So the dot product attention, as we saw, it will always be memory bound for decode. So we can then get the latency for dot product attention as how much data do we move around from HBM to the shared memory or the execution units of the GPU upon the total memory bandwidth. And this we do because, just a minute. So this we do because 4BD, the other reading the Q projection and writing AV result, those are much smaller than reading the KV cache. And because every sample in the batch has its own KV cache, so we have to multiply it with the batch size. For the linear operations, we saw that for small batch sizes, they will be memory bound. And the latency of linear operations, so by MLP, it also encompasses the linear projections in the attention module. That is the size of the parameters upon the memory bandwidth. And we do this because if we go back to this calculation, so we saw that we transfer activation beats and output in linear projection, but because we assume that D and F are much bigger than S, so the denominator came to be 2 times DF. Sorry. So it's the size of the parameters. So DF is the number of parameters and 2 is for PF16. So whatever parameter size is there about the memory bandwidth. For large enough batch sizes, the linear operations can become compute bound. And for that, we see how many flops are happening for that. And we divide it by the peak throughput of the GPU. So the total latency, the total inter-token latency, because it's the decode phase, is the sum of attention latency and the MLP latency. So we can write it in this way. And the MLP latency, depending upon which is greater, we account that for ITL. So depending on the batch size, either the MLP latency will be this or this. And notice that we write here minimum inter-token latency because this is a theoretical minimum which we're deriving. In practice, the ideal inter-token latency is likely to be higher than this because of many other factors like, let's say, network latencies and other things. For the throughput, the maximum throughput, so it's an upper bound on it's a theoretical upper bound on the throughput, which is given in tokens per second. It's batch size upon inter-token latency. And to see why batch size is there in the numerator, consider the fact that if B was 1, then the throughput would be 1 upon inter-token latency. But let's say here B is equals to 4, so at every step we are receiving 4 tokens after a period of inter-token latency. So we get 4 tokens together. So the throughput increases by a factor of B. If we plot the latency and throughput with respect to batch size, we observe something like this. So let's go back to this equation. The inter-token latency, when the batch size for smaller batch sizes, linear operation is memory bound. So we consider this factor. The attention latency increases linearly with the batch size. For larger batch sizes, when linear operator becomes compute bound, then this slope gets added to the linear dependency on the batch size. So in effect, the latency always increases with batch size, but it increases more sharply at higher batch sizes. So here MLP is in memory bound, and here MLP is compute bound. For throughput, we observe that at smaller batch sizes, the linear projections, the linear operations, they benefit from the fact that whatever weight gets loaded from HBM to shared memory, that can be used for a larger number of samples in the batch. And because the KV caches are smaller as compared in this regime, the KV caches are still smaller than the number of parameters. So by KV cache, we mean KV cache of all the samples in the batch. So the throughput increases with the batch size, but only up to a point, and afterward it plateaus, because here, as the batch size increases, the total KV cache size is also becomes quite large, and so that starts in a way dominating. So with increasing batch size, we can only increase throughput. We have diminishing returns on that. This is This is some experimental results from this paper on palm models, on different sizes of these models, both quantized and non-quantized versions. Here we are plotting on the y-axis cost, which is inversely proportional to throughput. B here stands for the batch size. C is for the number of TPUs, which right now we can ignore for our analysis here. And we observe that for all the models, as we increase the batch size, the latency decreases, but at higher batch sizes, the latency increases with increasing batch size, and it starts increasing more sharply with higher batch sizes. So latency is the x-axis. For the throughput, we observe that there is diminishing returns. So it increases more sharply initially, but then it plateaus the throughput. And if we are concerned about, if we have offline inference, then we would like to maximize the throughput and we don't care so much about the latency. So we probably want to go for higher batch sizes, the highest we can accommodate on our GPUs. For interactive applications, we probably want low latency, but we also want a decent amount of throughput so that in terms of cost, the service can be feasible. So there's this trade-off between throughput and latency. Usually one decides upon what is the permissible latency, and then they select the batch size so that they can maximize the throughput without going beyond the critical latency requirement. So even though a batch size of 1 maybe gives us the minimum latency, the GPUs are so underutilized in that case that it's not feasible to run the service with that. Notice how the curves are better for quantized version of the models. So for every particular point, the quantized version has low latency and higher throughput. The performance benefit comes from the fact that because the decode phase is usually memory bound, so if because of quantization, the memory footprint of waits and activations is smaller, so there's less things to move around in memory. So we are faster, we spend less time communicating bytes in memory. And secondly, also that usually the throughput of GPU or TPUs, they tend to be higher for the quantized versions. But also note that at the highest batch size, they basically perform the same. So let's think about, we have looked at the throughput and latency with respect to batch size. Let's also look at how much of memory requirement is needed during inference. So even before we do that, maybe first let's look at the training phase. So let's take a Gemma 9 billion model. From its report, which is given here, I pulled up these numbers. So it has these many layers, heads, embedding dimension, edge, head size, and so on. So during training, we would store the parameters in, let's say, BS16, and we would spend 18 GB for that. And when training, let's say if you're using an optimizer like Adam, then we would have two optimizer states for each parameter, the first and the second moment. And let's say that we are storing it in higher precision, FP32. So overall, we spend 74 GB for the optimizer states, which is much bigger than the parameters themselves. And for activations, let's say that we choose a scheme where we save only a subset of the activations. So reasonably, we can assume 1 GB for every sample, where a sample comprises around 8K tokens. So overall, we see that we are going to need multiple GPUs to fit everything in during training. Let's focus on the inference part and assume that we are going to have a quantized version of the model in int 8 precision. So with this, we need 9.2 GB for the parameters, and we don't need to save the optimizer state or activation checkpoints because we are not doing training. So for prefill, let's assume just one sample, and during the forward pass, we need to save some activation as we go along during the forward pass. So assume 8K tokens in the prefill stage, and for every token, the activation is of dimension D model, which is 3584. And because it's saved in int 8, so we need 30 MB for one sample to store the intermediate activation in the forward pass. And we can assume batch size even to be 1 because that's enough here to make the prefill compute bound. We didn't take into account the larger memory which would be required for the attention matrix because that is not materialized in the HBM because of flash attention. For the decode stage, for one sample, the activation needed is tiny, 3.6 KB. So it's basically 1 times 3584 times 1 bytes. But the KV cache for every sample is this much because so we have key and value matrices to store, and whatever data type size is, this is the number of heads, the attention head dimension, and these are how many tokens have already been processed in the cache before. And because we save the KV cache per layer, so it's multiplied by N. And if we do this calculation for a particular model in int 8, we have 1.41 GB per sample. So we saw before that we can improve the throughput at the expense of some latency for in the decode stage, but another aspect is that the KV cache is significant. So even for batch size being 7, here we are increasing the space taken by the parameters. Now we are in a position to actually compute the latency throughput numbers for a real-world model on a real-world hardware. So let's take Gemma 9 billion model, which we have been seeing now, and run it on H100 GPU. So we are considering the inference process, and we take the parameters quantized to int 8. Let's consider the decode phase just after the prefill. Immediately the next decode stage after the prefill. So we have already processed 8192 tokens. There is 80 GB on our GPU with this much bandwidth and this much tensor core throughput for int 8. So as we change the batch size, increasing from 1 to 128, the KV cache is basically batch size times 1.41, the number which we derived just a while ago. And the total memory is KV cache plus the space for holding the parameters, which is 9.2 GB. So adding up the KV cache with 9.2 GB, we arrive at these numbers. And this much space, ignoring the activations, the space for activations because they are very small during the forward pass, will need this much memory on the GPU for accommodating these many batch sizes. And we see that we can't afford to have batch sizes of 64 or 128 because it exceeds 80 GB. The latency numbers we derived from the formula which we saw earlier, and we see that it keeps on increasing with the batch size, which is consistent with what we had maybe reasoned from the formula. At the throughput as well, we see that it is increasing with respect to the batch size. And just to clarify that the latency and the throughput numbers, they were not derived from experimentation. Rather, these are theoretical bounds on minimum latency and maximum throughput. And the true value is likely to be higher for latency and lower for throughput. So we can only operate in the regime of batch size less than 64, so that's for sure. If we plot the latency and throughput with respect to batch size, we observe the behavior which we are expecting. So latency does increase linearly with batch size, and the throughput, it plateaus. So there's diminishing return to increasing the throughput. So the overall takeaway message is that we can't afford to have batch size of 1 to minimize the latency because the throughput is terrible. So we need to find a compromise so that the throughput is reasonably good, so that the hardware is utilized decently well at a reasonable cost, and the latency is also within limit. So we increase the batch size, the throughput only increases up to a point, but the latency keeps on increasing, and we might not be able to even accommodate larger batch sizes on whatever GPU we have. I just wanted to show a sample calculation for a batch size of 32 with this. So we derive the attention latency assuming that it's memory bound. So this is the cache size for a single sample multiplied by the batch size. This is the memory bandwidth, and we get this number for the MLP latency. This is assuming it's compute bound, and this value is assuming it's memory bound. So it's 9.2 GB divided by the bandwidth, and this is how many flops you would have to do divided by the peak throughput of the tensor core. And we see that for the linear operators, so by MLP I really mean all the linear operators in the self-attention and MLP. So this they are still memory bound at this batch size. So the decode latency is basically sum of this and this, which is around 16.22 millisecond, and the throughput is basically batch size upon latency, which is this number. That's all for this lecture, and let's continue on another topic in the next lecture.